welcome to today's session. I'm going to continue with the course by Camille. So please.
Thank you. So yesterday we had a long discussion about what is a singular of a foliation. And today I'm going to show you the hidden snakes, because now you know that there is a snake hidden under these leaves. It's there. And my goal is to warn you about these difficulties so that, again, next time you will see a singular of a foliation, there is no way you cannot see it. There is no way you can unsee it. So today's are hidden structures behind singular of a foliations. So, what kind of hidden structures are there? And somehow it's similar to Poisson geometry. It's kind of similar to the hidden structures behind a Poisson bracket. Similar, but still different. Well, what Poisson geometers would like to have, well, I know Henrique hasn't spoken about this yet, but we know we have a Poisson structures. Behind it, there is a algebroid on T star M. So I think we would like to have the same, like behind a singular foliation, we would like a algebroid. But in fact, we don't. We just get an almost algebroid. Something, as I will explain. When algebroids, good points, that at each point you have an oncome up, well, you have an oncome up, and the kernel of that oncome up is a algebra. So when you have a algebroid, like Poisson structure, at every point you have a algebra. This still works, fine. We see on the Redakis-Candalis construction, at each point of a singular foliation, there is a natural Lie algebra called the Isotropy Lie algebra. Good point with Lie algebroids is that if I take a leaf, it restricts to, I mean, there is more than that. I mean, not only there is a Lie algebra at each point, the kernel of rho, but if you restrict to a leaf, you get a transitive Lie algebroid. Why am I saying that? It's because for singular foliation, it's going to work in exactly the same way. On each leaf, you are going to have a transitive Lie algebroid called the holonomy Lie algebroid. This has been quite studied, for instance, by Androidakis and Marco Zambon. And of course, we would like to have a Lie groupoid. So from now, AS just means Androidakis-Candalis, because I'm going to say many times Androidakis-Candalis. Sometimes I just say right AS. Well, we would like to have behind a singular foliation, exactly like behind Poisson structure, we would like to have a Lie groupoid. You know, it's more or less the case for Poisson structures. Behind every Poisson structure, you have, or you don't have, but anyway, it was an old problem solved by Marius Kreinig and Fernandes, that you have more or less a symplectic groupoid, which is a Lie groupoid. What happens for singular of a foliation? Well, we still have a groupoid, but it's not a Lie groupoid. It's called the holonomy groupoid, and it's longitudinally very good, but transversally very nasty groupoid. I'm going to explain this. And it's not a Lie groupoid. It's much worse than in Poisson geometry, where you have this map from pi2 of the leaf that Kreinig and Fernandes constructed from pi2 of the leaf to something. And the image of this map is discrete, is Lie. So it's kind of more or less Lie. Here it's much worse than that. I mean, the singularities are far worse than that. And it's really this groupoid. So I'm not going to just present things I'm not going to speak about. This holonomy groupoid, this non-commutative geometer, Androidakis-Candalis, Debord, and others, we use it, in fact, to construct something I will not speak about, which is C-star algebra. And out of this C-star algebra, they do very strong analysis. They compute indexes. Well, I just skip that. I just say that there is a huge continent of analysis there. Well, no, I hope I won't be like a stamp collector if people who are fascinated by stamps, they can speak during a long time about stamps without realizing that their audience just don't have any interest into stamps printed in Tsar Republic in 1946. And well, my equivalent of that is that, okay, there is mostly algebroid, but there's also universally horrible algebroid. By horrible, I mean just lengthy algebroid, which are also called Q manifold, which are also called DG manifold, positively graded DG manifolds. So probably today I won't speak about that. I will speak a little bit about that on Friday. And well, I hope it's not just like stamps, but there is a universal lengthy algebroid. I wanted to make at least this point. So I've always been told that, okay, where is it? Anyway, let us come back to the definition a little bit. I think it's important. Just to remind you what we did yesterday. We just had a long discussion about smooth or partition manifolds and blah, blah, blah. But at the end, I end up by saying a singular foliation on a smooth manifold M, it's a subsheaf. If you don't like sheaf, it's local. So on each open space, you have vector fields, calling them F. And you want F to be involutive, so F bracket with F inside F. You want F to be symmetry of M modules. So if I have my vector field rated, which means near any point, I have x1, xr in F, so that F is a linear combination of the xi with coefficients being of the functions. I think it's important to remind this definition. You have alpha, beta, and the gamma. 3 points. Okay. And something else I said is, well, just to remind you, oh, it's not the one I wanted to have, sorry. It's this one. An important point is that singular foliation defined as have defined them indeed have leaves, indeed induce a well-defined smooth partition manifold, which can be, whose leaf can be seen as all points you can reach starting from a point, what I call R leaves, or from sub-manifolds whose tangent space is precisely obtained by taking the tangent space of F, which means the subspace you get by evaluating at that point all vector fits in F. And to prove that, I told you that the hard point was to show this thing. Well, the easy point somehow is to show that there's a Weinstein splitting like a theorem. But the hard point, in fact, is to show that if you have a vector field in F, assume to simplify its flow is globally well defined, then its flow is a diffeomorphism from M to M that maps F to F. So the flow of an infinitesimal symmetry of an element in F is a symmetry of F. And so it's a hard point. And I didn't do the proof. There's an elementary proof. And today I will give you a more elaborated proof that uses the notion of almost real algebra. Okay. I think it's good to start by reminding what we did the class before. Okay, so what do we have when you have a singular foliation MF? What kind of hidden things do you have behind it? Well, at least we would like to have a vector of a bundle. So definition, an anchored of a bundle. When I say the word anchor of a bundle, I just mean I have a vector bundle. So for me, a vector bundle have finite rank. Okay, I don't want infinite dimensional one. And the map called anchor from A to Tm. That's just anchored bundle. But those we are interested in are those which are over F. And over F, what does that mean? It means if I take all sections, maybe compactly supported sections of A, I apply the rho, and I get F. Or if I think in terms of sheaves, I take sections of A, it's a sheaf, I take the image, it's a pre-sheaf, I sheafify it, I get a sheaf, I want this sheaf to be F. If you haven't understood what I've just said, just think a dog was barking during a few minutes, it doesn't really matter, okay? Okay, so does this exist? What do you think? Do you think anchored bundle, oh, it's a proposition, in fact, on the slide, it's stupid. So, well, it may not exist globally because I'm sure that if there's an anchored bundle where the fiber have dimension 17, the number of local generators is obviously bounded by 17. I take just local trivialization of A, I take the image for the anchor, I get generators. So if it's locally finitely generated but not globally finitely generated, the answer is no. But at least in the smooth case, that's the only problem we can have. And in the holomorphic case, it always exists locally. So any smooth singular of a foliation admits a non-chord bundle over it, at least if it is globally finitely generated. So if I have global generators. Okay? So locally, it always exists in particular. Okay.
Sorry.
Yes. Where?
The actual bundle over F.
Yes.
So what was it?
Oh, F is a singular of a foliation.
Oh, okay. So what does it mean to be over F?
Oh, it means that. It means that if I take all sections of A, I apply anchor, I get the safety module of the vector fields. I want this module to be exactly F. Okay? So again, proof. Well, assume you have generators x1, xr. Let x1, xr be generators. When I mean generators, I mean over C infinity of n of F. How can we construct? Is it normal with screen? So how can one construct an anchored of a bundle? Who has an idea? I want to construct a vector bundle first. What can I do? Well, I just take the trivial bundle. Typical fiber RR. Then I introduce a notation, which is always a bit complicated. I know it's getting confusing. I just call EI the ith trivial section of this guy. The section mapping M to 0, 0, 0 everywhere except 1 here and 0, 0, 0. And here it's the ith place, comma M. Okay, I know this notation is very confusing, but when you have a vector space, RR, you have the canonical basis of that vector space, and you can do the same when you have a trivial vector of a bundle. I just denote by EI the ith trivial section. Okay, and then just define rho by rho of EI equals xi plus extend by safety of M la linéarité. Now, I have defined, provided I have given global generators x1, xr, this defines an anchored bundle over F. Is it clear at this point? I'm saying that because I'm going to repeat this kind of argument many times. Okay, so anchored bundle exists.
Are you assuming that there are
Yes. Yes, exactly. So if it's globally finitely generated. Oh, you may argue. Okay, so here what I have proven, in fact, is that I've proven that if there exists, if F is globally finitely generated, then there exists an anchored bundle. Okay, that's that direction I have proven. Yes.
If I understand it correctly, it's different from saying that rho of A is a distribution tangent to the foliation. Right?
This is different. Yeah, I can give you a counter example.
Right, because that all, so the tangent distribution always admits an anchor vector bundle. I think that's true.
Yeah, I think that's true. Yeah.
Okay.
Yeah, no, it's different. Yes.
The reason why we need them to coincide and not just being like.
In fact, if you look at notes, I define both over F and inside F.
It's not necessary.
Yeah. Oh, yeah. By the way, it's something I'm quite often arguing with differential geometers. But to prove the direction, you have to know a result, which is not so trivial. But if I take any vector bundle on any manifold, the sections of this vector bundle, in fact, is finitely generated as a symmetry of M module. Why? Because any vector bundle has another one, so that the direct sum is the trivial bundle. The trivial bundle is obviously finitely generated, and you project on the initial bundle. So that's why it's uniform only.
Example where it's not globally finitely generated?
Yes. So I owe this example to Marco Zambon. Maybe Alexandre Deck is also in this paper. Well, you take points on R2, and you take vector field that vanish here, then that vanish at order 2, so that vanish together with their derivatives, then vanish at order 3, then vanish at order 4, and so on. Here you take vector fields that vanish at order n. And well, if you look at the idea of a function vanishing at order n on R2, this has n+1 generators. So vector fields, since there is d over dx or d over dy, it has two n+1 generators. You see, around each point, it's finitely generated. But globally, it's not just because the number of local generators goes to infinity. Very good question, yeah. By the way, I can do that in holomorphic also, the same problem. But I mean, it doesn't come for very expensive to say that it's the same. So fine, I'm more or less proven that at least around the point, or quite often globally, first structure we have behind the singular foliation is an anchored bundle. That's very weak. Like, so far I haven't used brackets. I could do the same for any symmetry of M, submodule of vector fields. And it's a question that will come every time today. Second problem, it's very nice to have a structure behind a singular foliation, but does it make sense? Is it independent from the construction? Okay? Well, so I have to define equivalences of anchored the bundle, and to say, oh, two of them should be the same. So first, what are morphisms of anchored the bundle? Obvious thing, it's just vector bundle morphism over the identity of M, such that it behaves with respect to the tangent map. Oh, it didn't appear. It should be equal here. It shouldn't be an arrow, it should be an equality. Okay? Why does it appear? Okay. Well, then you say that two such morphisms are equivalent if they coincide after you apply the tangent map on the arrival space. And if you accept that as being equivalence of morphisms, well, what does it mean equivalence of anchored bundles? So I have my two anchored bundles, A1, A2. I have a morphism this way, I have a morphism this way. And if I compose them, I want this to be not the identity, but be equivalent to the identity. Same thing if I compose them this way. Okay, so there is natural notion of equivalence of anchored bundle. And well, not hard to prove that any two anchored bundles over the same singular foliation are equivalent, in fact, in the sense I have given before. So that's probably the first hidden structure we have behind a singular foliation, at least globally generated one. An equivalence class of anchored bundle, and it would be often like this. Sorry? It's sometimes it's very stupid. I have phi psi. I want, in fact, it's just to say that phi psi of any x minus x, if I apply rho, I get 0. And same thing with psi phi. It's very stupid definition. So, but having an equivalence class of something is annoying, right? We would like to have something more concrete, like a vector space. So for that, I'm going to say something very basic of differential geometry. I'm going to say that if you have a vector bundle morphism over the identity phi from A to B, you choose a point, we have two different definitions of the kernel of phi at this point. You have the ordinary kernel, sometimes called weaker kernel, which is just the usual one. I mean, you take phi m, you have phi from A to B, it restricts to a vector bundle morphism phi m from AM to BM, and you take the usual kernel of this map. Okay? And there is a more sophisticated one called the strong kernel. It goes like this. I haven't defined it here. Strong kernel at M of phi at M is this. It's elements in the fiber IM such that there exists a local section I tilde in section of A through A, which is in the kernel of phi at every point. Okay? So it's not just a point which happens to be in the kernel of phi at this point. I want to be able to find a local section which is in the kernel of phi at every point. Okay? Like if you think of the Poisson structures, the differential of a Casimir is a strong kernel of pi dash. Okay. Well, of course, the strong kernel is included into the kernel, and they behave in very different ways. Like if I have a sequence of points that converge to this point, yeah, assume the ordinary kernel has dimension 5 on each one of these points. At the limit, the dimension cannot be 4, maybe 5, maybe 6, maybe 7. It goes up. The strong kernel is the opposite. It goes down. If it's 5 at every point here, when I converge to my point, it goes down. So if it's 5 at every point, it can be 5, it can be 4, 3, 2, 1, 0. It cannot be 6. Okay, so one goes down, the other goes up. Which means that when they coincide at a point, they coincide in a neighborhood, and somehow that vector space is a measure of how singular is this vector bundle morphism at this point. Yeah, how far away it is from being just a constant rank map. Okay? So here, I mean, 0 on the dense open as a subset, and blah, blah, blah. So, if we apply this to a non-code bundle, what do you get? What you get is that on regular points, on regular leaves, the kernel of the anchor map, the strong kernel of the anchor map are the same, and that quotient space is 0. But on singular leaves, this quotient may not be 0. Okay, so let us call isotropy space at a point M the quotient kernel of rho divided by strong kernel of rho. Okay, it's a vector space. At regular point, 0. At singular point, never 0. So, okay. Well, that at least an invariant in the following sense. Easy to check. You know, my definition of equivalence of anchored bundle seems kind of sloppy. I mean, it seems very, very weak. But at least, if two anchored bundles are equivalent, this quotient is the same. That's easy to prove. So this vector space is canonically attached to the singular of a foliation. I can take whatever anchored bundle behind, I make this quotient, I get the same vector space. I get canonically isomorphic vector space, and it's the dimension is canonically attached to the singular foliation at this point. Okay, so this vector space doesn't depend on any choice, but the construction that, as I said, is canonically attached to the foliation, and a theorem. I think I saw it in Dazor paper. I think it is on Androidakis Scandalis. Well, now I have three integers attached to a singular foliation f on the point M. I have three integers. One of them is a dimension of the leaf through M. It's a manifold, has a dimension. One of them is a dimension of this isotropy vector space, Gm of f. There is one that comes from the fact that it is locally finitely generated, which means that I can make sense of the rank of f as a symmetry of M module as being the minimal number of these local generators. That's a general thinking sheaf of theory. It's locally finitely generated, the rank makes sense. It's a minimal number of generators. So the rank of f at M makes sense. And you can prove that the rank of M is a dimension of the leaf plus the dimension of that vector space. Okay, these three integers are linked. Okay, so yes.
Can one modify the notion of morphism to be vector bundles so that the strong kernel is the categorical kernel?
Categorical kernel, what do you mean?
The categorical kernel, I mean,
if you like,
that's an exact sequence of that, you have 0 going through the kernel, going into the.
maybe I'll answer. Okay, this guy, this vector space, it's store of f r in the symmetry of category symmetry of M module. I think that answers your question. See, that vector space, like it's a Tor functor applied to f and r seen as a symmetry of M module by evaluation at this point. If you don't know what Tor functor is, just forget it. Okay. Okay. So, all right. So now we have. Okay, let's go back to anchored the bundle. What kind of structures do they have? What we would dream of is that we will have to get on the anchored bundle a Lie algebroid. We have the anchor. Can we get the bracket? So I've been told yesterday Lie algebroid hasn't been defined yet. So Lie algebroid, in one word, it's a Lie algebra bracket and sections of A that satisfy Leibniz condition, so and Jacobi identity. Okay, so the dream would be to have a Lie algebroid structure. Does it work? Well, no. Well, it seems to work because look. How could I define on this trivial bundle? How could I try to define the algebraic structure? Well, I have to define the bracket of two sections, EI, EJ. It has to be the sum with some coefficients of the generators. I already know the anchor. So if I know the bracket on generators by Leibniz, I know the bracket everywhere. So how to do that? Well, just think, the xj are generators. So the bracket is in F, so the bracket has to be written like this. Okay. For some functions, be careful now. These guys are functions on M now. They are not like Christoffel coefficients. They are not reals. They are not elements in the field. They are functions. I think I have lost everyone. So, how could I try to define a algebraic structure? Well, I just say, oh, I have generators x1, xr. So x1, xi bracket xj, by involatility, it's in F. So xi are generators, so xi bracket xj is the sum from k equals 1 to r ofcijk xk for some functioncijk. Okay, so let us define a algebraic bracket like this. I take the same functionCijk, and I declare that the bracket of a trivial section EI with a trivial section EJ is that sum. Well, two problems. Here, these guys, they are even not skew symmetric in J and I. Right? A priori, they are not skew. So this bracket may be even not skew symmetric. You see? Do you think? No, why? Well, sorry? Well, all I know is that xi, xj, it's in F, so it's some linear combinations of the xk. But some linear combination, I have no condition a priori on these guys. Okay?
What is the bracket that you have over there? Is that the usual bracket of vector fields?
Here, yes.
That is symmetric, right?
Yes, but if I then define abstractly the bracket like this, does that need to be skew symmetric expression? Exactly. Right? I mean, I'm just using axioms of being a singular foliation. I take xi, xj, it's a linear combination of these guys, some coefficients there. I have no condition on these coefficients, a priori.
You could as well answer this, right?
Exactly. That's what I'm going to do.
Three images of xi and xa by the anchor.
Excuse me?
What's the relationship between EI and xi? You're choosing three images.
Yeah, rho of EI is xi. That's how we define the anchored bundle.
No, I understand, but you have to choose an EI, right? I mean,
Yes.
I mean,
Yes.
You know, it's a choice.
Absolutely. Yeah.
More than one.
Yeah, absolutely. Yeah. Yeah. So skew symmetry is not a problem because I also have this. Right? I just invert these indices. This is 1, this is 2. I take 1 minus 2 divided by 2, and I get xi, xj equals same thing, but now I have cij minus cijk with 1/2 xk, and these guys are skew symmetric. So if I use this guy here, it's minus. I use this guy here, at least the bracket I define on section of A is skew symmetric. But does it satisfy Jacobi identity? Do you have this? That's a hard one. Well, you should, because look, here you have a Jacobi. These are just the vector fields. But when you look abstractly here, this bracket defined like that, and you compute the Jacobiator, you don't get 0. You get an expression where if I replace each one of the EI by xi, we get 0. But we don't get 0. You see? So Jacobi does not hold. Is it clear? Okay. I didn't intend to make this computation, so maybe I skip that part. So do we get a algebroid? No. And So again,
What you're saying is that the Jacobiator is in the kernel of the anchor.
yes, all you get is that the Jacobiator is killed by the anchor map. So the dream of having a Lie algebroid is not true. And in fact, let me ask one of the most basic questions I know on singular foliation. So Friday will be all about open question. And here is the most scandalous one. No, the worst one. Nothing to do with scandalous. Just take vector fields on R2, just R2, that vanish quadratically at 0. Vanish at 0 with their derivatives. Yeah, that's a singular of a foliation. We saw it yesterday. It has 6 generators. Does there exist a Lie algebroid? So the question, by the way, is first cited in a paper by Androidakis and Marco as a Zambon. Does there exist a Lie algebroid, a row, such that, which is an anchor map bundle over A, so that row of sections of A is exactly F2. You see? That's almost the most stupid singular foliation you can think of on R2. The most stupid one is singular foliation vanishing at a point. The second one is vanishing quadratically at a point. Right? Just is there a Lie algebroid on R2? I mean, no need to go to complicated spaces, so that the image of the anchor map is precisely those vector fields. Yeah, sorry to have spoiled the next night. But it's pure scandal that nobody can solve this problem. Right? I can prove that there is no one of rank 6. Anyway, so, oh, what have I made? Okay. So, we don't have a Lie algebroid. Too bad. Almost 20 minutes. Okay. We don't have a Lie algebroid, but we have at least, by this construction I have shown here, you have an almost Lie algebroid. What does that mean? You have a skew symmetric bracket that still satisfies a Leibniz. Jacobi is not true, but at least the anchor map is a morphism. So this bracket is almost nothing. It's not Lie. But if I apply the anchor map, it's a morphism to vector fields, which is Lie, which implies that the Jacobiator is killed by the anchor map. So the Jacobiator at point is included into the, is killed by the anchor map, so it is in the strong kernel. Okay, so the Jacobiator is by the strong kernel. Good. Well, what does this imply? Well, using this almost Lie algebroid structure, I'm going to explain you how you can prove that vector fields in F have flows which are symmetries of F. I come to that soon. Yeah, I know. But it also implies that this isotropy vector space, in fact, they come with a Lie bracket. Why? Because the isotropy vector space, it's kernel divided by strong kernel. Okay? And if you have an anchored bundle, because of this anchored condition, it's because of Leibniz, it's easy to see that the bracket you have, which is defines the level of a section, that you have a Leibniz. So it induces a bracket on the kernel of rho at a given point. Again, not a Lie bracket, just a bilinear skew symmetric map. Okay? And as we say, the Jacobiator is valued in the strong kernel. So this bracket is not a Jacobi, but if we curve modulo by the strong kernel, it becomes a Jacobi. Also easy to check that by the anchor condition, the strong kernel is an ideal of your bracket. Okay? So you get that this isotropy vector space has a Lie algebra structure. And it's easy, we can prove that this Lie algebra structure, again, it's not arbitrary. I choose an uncut bundle, I choose an almost Lie algebroid structure. There are choices. But this space is canonical, and this bracket is canonical. It doesn't depend on any choice made in the construction. And, in fact, it's a proof. Why is it canonical? It's because, in fact, it coincides, and it was the original definition. So proof of 2 and 3. Well, I'm going to define you a Lie algebra. I take f of m. It's all x in f that vanish at the point m. Okay? So f of m is included in f, and it's clearly a sub-Lie algebra. Then I take IMF. So IM is all functions. That's the idea of all functions that vanish at m. IMF, clearly that's a Lie, that's included into f of m, because they vanish at m. It's included, and it's a Lie ideal. So the quotient space is a Lie algebra. And it's not even hard to check that this vector space, in fact, as a Lie algebra, as a vector space on the Lie algebra is canonically isomorphic to this quotient. Okay? And it is the original definition in Androidakis-Skandalis article. Okay. What I did to a point, I could do to a leaf. Take a leaf. Yes, sorry, that's not like. Take a leaf. L. You have your uncut bundle on the leaf. You have your uncut bundle. You restrict to the leaf, and you divide by the strong kernel at each point. You may say, "Oh, that should be absolutely a horrible quotient." No, because as I say, every 2 points on the leaves are kind of the same. So in fact, there's a dimension of the strong kernel is going to be constant along the leaf, so the quotient is going to be a very good vector bundle. And in fact, this vector bundle comes equipped with a transitive Lie algebroid. Whose isotropy are these Lie algebras? Okay, so if I have a leaf, I do this construction and get transitive Lie algebroid. I take the almost bracket. I restrict and I make this quotient by the strong kernel. I get a decent Lie algebroid, which happens to be transitive. Again, it coincides with a Lie algebroid that appears in Androidakis-Skandalis and has been studied a lot by Androidakis and the Zambon. The sections of this Lie algebroid, you can see them algebraically as being f divided by f times the ideal of functions vanishing on the leaf. Okay? So you have a very one-line description of sections of this Lie algebroid called the holonomy Lie algebroid. Okay, so before I arrive to holonomy groupoid, one more word. I still wanted to explain the idea of how we can prove that just the idea of how we can prove that flows of vector fields in F are a symmetry of F. How we can prove that? So I'm going now to 1. Yes? And of
I don't see the relation of the right-hand side A over the side that
here? Oh, I just take at each point, I take the strong kernel and I divide. Yeah, so how do we prove A? Well, in fact, what we are going to prove is that I take X in F. I take a section A whose image by rho is X. Okay? And my claim is that because I choose an almost bracket, and my claim is that adjoint action by A, which goes from sections of A to sections of A, is going to induce, by some very general trick that won't be surprising if you know the algebroid, is going to induce a linear vector field on A. So just forget A is a vector bundle. You are going to have a vector field here, call it A hat. Okay? This vector field being a linear, I'm not saying the definition. It means that its flow is a vector bundle morphism. Its flow is vector bundle morphism. Now, almost, what is going to imply is that these vector bundle morphisms extend just rho and rho. So it's not only a vector bundle morphism, it's a non-chord bundle morphism. And there are a trick to prove it. And since it is a non-chord bundle morphism, in particular, we just write down the definition. It means it maps F to F, because it maps sections of A to sections of A in a way that commutes with rho. So that implies this implies that it's a symmetry of F. See, it's a funny proof because we use almost bracket, which seems to be almost nothing as a structure. And we use it still on the algebraic kind of techniques to prove that there is a morphism. Okay. Yeah, well, yeah. Okay, here I assume F globally finitely generated. If not, you have to be a little bit careful, take open sets and blah, blah. Globally finitely generated. From now on, in fact, I won't use this. So. Second part. Now I want. So I come to my last question. So for a Poisson structure, up to obstructions formed by Kreinig and Fernandes, you have a symplectically groupoid. What happens for singular foliation? You have a Lie groupoid behind it. And now what I'm going to speak of is Androulidakis Skandales holonomy groupoid. Okay. What is that? I start with an example. I take vector fields on Rn vanishing at 0. I get two things. You have two leaves, right? 0 on Rn minus 0. And this groupoid is a disjoint union of the pair groupoid Rn minus 0, Rn minus 0 to Rn times 0 and GLM, which is a Lie group over M. See, it's not that complicated. Again, I have think R2, I threw 0 away. Over 0, I have GL2. On the rest, I have the pair groupoid. But in fact, there is more. Because when you say that, we forget that there is also a topology. So there is a way to glue these two spaces. See, it's not just there is this groupoid and there is this groupoid. No, we have to glue them. Okay. So we define it slowly. So I'm going to do three things. Bisubmersions, then restriction of the holonomy groupoid, and I will give the theorem by Claire de Boer about smoothness, relative smoothness of these groupoids. Because this groupoid, so it appeared in the paper by André Scandales, but Claire de Boer somehow did the de Boer case, the projective singular foliation, first, and after she proved that it's kind of smooth in some direction. Okay, so step by step. On my, how do we say in these cases? I'm not going to finish this today, but it's on purpose because on things, if I have to repeat on Friday, I remember better, something like this. I'm probably not, I intended to finish there, but I probably finish there. Yep. It's over, oh yes, sorry. Over zero, just a Lie group over zero. But notice that that's certainly not Lie when you look both of them all together, like the dimensions don't match. But on each leaf, it's Lie. And this is going to be the Boer smoothness of the theorems. But on each leaf, at least it's smooth. Okay. So, my, what do we say, field director? I forgot to check the translation, like red wire. Is it like in Poisson geometry? Is it like for Poisson? Like, is it like for groupoids, for Lie groupoids? So first, I'm going to introduce Bisubmersions. Okay, and from now on, F is a smooth singular foliation on F. So definition, bisubmersion, blue, right? Red. Bisubmersion. Bisubmersion don't make sense alone. It's over F with a triple X, M, X, S, and T, with this guy is a manifold. These two guys are submersions. Maybe not surjective, by the way. And, well, that's why it's called submersion. I have X and I have two maps, source and target, by the way, which are submersions. But you have conditions, of course. Three conditions. Well, I told you yesterday, one of the elementary operations that work with singular foliation that they can be pulled back. As a smooth distribution, you just get the new leaves and the pullback are just the pullback or just the inverse image of the old leaves. As a vector fields, basically, you take the vector fields here, you lift them in an arbitrary way, and you add all vertical vector fields, which are tangent to the leaves. Okay. So, where did I at 1, 2, 3? Sorry. Such that I want that if I pull back F by the source, I want this to be equal to the pullback of S by the target. Okay? That's not enough. There is a last condition, very important. I want this to be kernel of TS plus kernel of TT. Sections of this. What's that? It's all vector fields of the form X plus Y, if X, Y in vector fields on X, such that X is a section in kernel of TS, Y is a section of kernel of TT. Okay. So is it like groupoids or not? Well, few things are quite similar. Have a map, a manifold, sorry, and you have two submersions, X, S, and T, right? So it looks similar to groupoids, but you don't have units and you don't have units, but this is okay. Definition, a unit is a map epsilon from M to X, which is a section of both F and T. So that S epsilon, T epsilon equal identity. Well, it may not exist, but I can define it. Okay? So if I have a bisubmersion which has a unit, it's more and more like Lie groupoid. You have source, you have target, you have a unit. But you don't have this product, right? So it's similar, but still quite different. So you're probably asking for examples. What was the first example you have in mind that should work? Sorry? You know, something which has a source and target should be a bisubmersion, have even a unit. Groupoid. The groupoids are bisubmersions. It's hard, it's not easy to prove. Good exercise. Really, not easy, but it's true. It's not that easy, I mean, it is true. And by the way, what's that for Lie groupoid? You take all left invariant vector fields, you put all right invariant vector fields, and you take the symmetry module, symmetry of gamma module they generate. It gives you exactly that. Second example is called the fundamental. The fundamental bisubmersion. I give two versions of this. It's like this. So you have a map from RR times M. Take RR times M. It's not X yet. Okay? And I will do two things. Source will be a map to M, just projection. And the target will be that. Well, I map lambda 1, lambda R, M to the image of M through the flow at times 1 of sum of lambda I xi, where I forgot to say that x1, xr are generators of F. So I take generators of F, and I define on this trivial bundle two maps, projection on M, and the outcome of the flow of sum of lambda I xi to M at time 1. That's not a submersion, but there exists a neighborhood of 0 where it is a submersion. There exists a neighborhood of 0 where X is a bisubmersion. It's called the fundamental. They call it the chart, in fact, but just rename it the fundamental bisubmersion. Well, I think if you know Poisson structure, you won't be surprised that you can take, in fact, any anchored bundle. S, you just project A to M, and T, from A to M, you take the spray, Kreinig and his collaborators ID, which means you choose a connection on A, and you choose row paths which are parallel with respect to that connection. Exactly the same as Poisson spray, but for anchored vector, a bundle. And you look at the endpoint. endpoint of the spray is the same thing as that, just made more abstract. And again, there is a neighborhood of the zero section where it is a bisubmersion. Okay. So groupoids and neighborhood of zero section in anchored bundle to make our instances of Bisubmersions. I have 1 minute. So I'm just going to say two things. I continue on Friday, very late. Well, holonomy groupoid to be continued on Friday, but we continue actually tomorrow in Ruben's exercise class. I will finish as a question he will answer. Well, okay, you don't have a product, you don't have an inverse on a bisubmersion, but you have kind of. Take a bisubmersion and take a second one. ST bisubmersions. Okay. The two things. We call X minus 1. The bisubmersion is the same one. Just S became T, T became S. I call it the inverse bisubmersion. Okay. And I can take both of them. I take a composition. It's just fibered product. Y times M, X times M, Y over T on S. And I project by S and by T on M. Composition of two bisubmersions is a bisubmersion again. Inverse, it's obviously a bisubmersion again. Here you have something to prove. Here it's trivial. So it's a bit like product and inverse for groupoids. Right? At least you can make product, maybe not of elements in bisubmersion, but of bisubmersions. And inverse, maybe not of elements of bisubmersion, but of bisubmersions themselves. Now, we call atlas. Oh, sorry. You have an equivalence of bisubmersion. I just make the picture. If you know more equivalence of groupoid, very logical. You say they are equivalent. If only there is a third one, commutative diagram like this. Just think Morita equivalence of groupoid, it's the same. Yes? Yes. Okay. And call an atlas. It's a bisubmersion such that X minus 1 is equivalent to X, S times X is equivalent to X. Okay. And theorem, I have an atlas and I divide by an equivalence relation, which is identify 2 points if they have a neighborhood where they are equivalent as bisubmersions. This is a groupoid. And well, if I start with a fundamental bisubmersion, I get an atlas just by taking all inverse on all products of the fundamental bisubmersion. I make this construction, and we get, yeah, the things. So question, and we get the Androidakis Skandalis holonomy groupoid. I will describe more on Friday. I'll just finish by a question that Ruben will solve tomorrow.
What is the map from N to X? That includes the map from N to X.
Oh, no, these are all. Just more equivalence of groupoids. That is the same. question, well, take all vector fields which are tangent to a sub-manifold of a manifold. What is the holonomic groupoid? All vector fields on M tangent to the W, find the holonomic groupoid. Thank you. I'm sorry for have spent more time. Give more details on that on Friday, and I will spare you a little bit more in the algebroids.
Okay, we have some time for questions now.
What exactly is the atlas?
So, an atlas is a bisubmersion which is equivalent to its inverse, so that the product of itself is equivalent to itself. And you get one like this. You take the fundamental bisubmersion, and you make all fibered products, where by zero, I mean it's either nothing, either inverse, either a -1. By construction, that's an atlas.
Why is it called an atlas?
Parce qu'on aurait des questions scandaleuses. Well, no, it's really kind of an atlas. Because it's not, yeah, I think the idea was really, it's a way to encode all local diffeomorphism from a point of M to another point of M that preserve F. So I think it's an atlas of all local diffeomorphism that preserve F, all symmetries of F. So it's an atlas of symmetries of F, somehow. Also, it's kind of atlas of the quotient. The quotient is not a manifold, but the best you can do, I think even Marcos, maybe it's even an atlas in the sense of, what's the name? You have manifolds and you have, well, the best you can have as an atlas for the holonomic groupoid.
Are there any other questions online? Just a couple things. So in your definition of bisubmersion, S and T are surjective or not?
Not necessarily.
Not necessarily.
Yeah.
And the other comment is that I believe there is another construction of this groupoid that it's more in the analogy with the standard construction for regular foliations using paths.
Absolutely. Absolutely. So there are even two such constructions. Yes, so you would like to say that the holonomic groupoid, it's like the construction you use with Marius Kreinig, like A paths up to homotopy. You would like to do that with almost the algebroid. So Villatoro and Garmendia did that, and they prove that they get back the holonomic groupoid like this. And with Lavaux and Strobel, we also did kind of things like that using the L-infinity algebroid, and we say, oh, take the L-infinity algebroid, take paths up to holonomy, and you get more, you get the universal cover, in fact, of Android-Active Campbell's holonomic groupoid. So yes, there are two descriptions by paths.
Yeah, Johan?
This transitive algebroid.
Yes.
So it's always integrable, and if they are they related?
Exactly. So if I take the Android-Active Campbell's holonomic groupoid, I mean, you have a whole construction, very complicated. At the end, I get a groupoid where the orbits are the leaves of F. Good. De Boer proved that this transitive groupoid is Lie. It's a Lie groupoid. And what is the corresponding Lie algebroid was the holonomic Lie algebroid of the leaf. So it matches. So if you want, the holonomic groupoid of Android-Active Campbell's is to take all the holonomic Lie algebroid of the leaves, you integrate them. You have to prove they're integrable. It's not easy. You integrate them all. And after you have integrated them all, you take a quotient, because maybe you have to quotient something, a discrete quotient, and you have to glue them. That's very surprising, actually, because there is a theorem, again, with Fernandes and Marius Krajnek, that say, oh, an algebra is integrable if only if a map from Pi2 to germs of diffeomorphism has a discrete image. It's absolutely not the kind of argument Claire de Boer uses. She uses arguments that are based on a theorem that if you have a compact manifold, or if you have a compactly supported vector fields, you look at all the periodic orbits. Okay? You throw away 0, because if you have a point where the vanishes 0 is a period. The theorem says that the periods are bounded below. Like you cannot have on a sphere a point where the period is 1/2, a point where it's 1/4, a point where it's 1/8. It's impossible. It's bounded below. It's very surprising.
If I can comment on that.
Yes.
So that's called the period bounding lemma.
Yeah.
It's a very well-known result in dynamical systems, and we use it in our proof.
Sure. Okay. Sorry?
Well, the mechanical code is when you try to
Vector fields on a bounded, on a pretty compact domain.
Yeah. Oh, sorry, so I didn't know you were using it.
All right. Any more questions? Oh, there's one down there. Sorry. Go ahead. Can you shout it out? If I can repeat your comment for the people that are online, I think your comment is that in your result with Orel Villatoro that Camille was mentioning, you used almost algebroid as a short. For the,
Oh, yeah. Yeah. Yeah, I agree. Yeah.
Any other comments or questions? If not, let's thank Camille once more.